Then it's an oscillating spheroid, like a ball of water wriggling in space. But what exactly is oscillating here? The event horizon seems to define the surface of the black hole, but it's really the fabric of space-time itself that's vibrating. The two inspiraling black holes make powerful space-time ripples, gravitational waves, which intensify as the black holes approach merger, only becoming observable in the last fraction of a second. And then the merged black hole continues to radiate these space-time ripples as it oscillates. But these quickly die away as the black hole settles into its final static form. This final phase is called the ring down, an expression that comes from the analogy with a bell. When struck, a bell vibrates with many different frequencies, many overlapping harmonics. As those vibrations give up their energy, in this case to sound waves, the vibrations fade and the bell rings down. A struck black hole also vibrates with many different harmonic frequencies. The harmonics of a vibrating sphere, be it a blob of water in 0G or a black hole, are analogous to the harmonics of a vibrating guitar string or piano wire. In the latter cases, we can describe a vibrating string as a series of standing sine waves of different frequencies, all happening at the same time. The lowest frequency the string can support is called the fundamental mode. It's usually the strongest or the loudest and defines the note, middle C, F sharp, whatever, played by that string. Higher frequency modes are called overtones. They provide richness and texture to the sound. The full set of possible frequencies a string can support are called its harmonics. The harmonic oscillations of 2D surfaces like drum skins, bells, or the event horizons of black holes are a good bit more complex than in 1D. In the case of the event horizon or any spherical-ish surface, we break down the oscillations not into sine waves, but into spherical harmonics. These are a set of functions pretty analogous to a 2D sine wave on the surface of a sphere. And each spherical harmonic can represent a single pure oscillation on that spherical surface with a set frequency. A harmonic oscillation that decays over time is called a quasi-normal mode. For a black hole, another way to think about its quasi-normal modes is as a set of gravitational waves trapped in orbit around the black hole. They leak away over time, but while present, they warp the shape of the event horizon. Okay, so a black hole can ring like a bell when struck. In that case, a black hole merger must be the biggest hammer strike of all. But what does the ring down of a black hole really look like? Well, we can answer that by asking what harmonics are present in that oscillation, and how quickly do each of those harmonics fade away. Many scientists had assumed that in order to see the overtones, you'd need to look at the tail end of the ring down, when the black hole was approaching a more spherical shape. They thought that right after the merger, the black hole would be too chaotic. The oscillations would be non-linear, or in other words, not well represented by adding together a simple set of spherical harmonics. The problem is, at the tail end of the ring down, the LIGO signals are probably too weak to detect the overtones. Matthew Geisler, Max Easy, Mark Scheel, and Saul Tucholsky of Caltech and MIT went against this prior assumption in their recent paper. They looked for overtones in the ring down from right at the point of black hole merger. Now, this wasn't a real black hole merger that they looked at. We'll get back to that shortly. Geisler and team first found the harmonics in a fake black hole merger, specifically a simulated merger by the SXS, Simulating Extreme Spacetimes project.
Yes.
Basically the result of teaching a supercomputer general relativity and, among other things, telling it to collide thousands of black holes. The advantage of first trying this with a simulation is, 1, you don't have to use a signal degraded by a billion years of travel, and 2, you know exactly what parameters went into the signal, in particular, black hole mass and spin. So you know if you got the right answer when you try to predict these values. The researchers found a few very surprising things. First, the waveform was nicely simulated by spherical harmonic oscillations right from the point of merger, so it was not the chaotic mess previously assumed. Second, when the ring down begins, some of the overtones are actually stronger than the fundamental mode, even though they do tend to die out more quickly. This means that these overtones are potentially detectable in the real merger signals from LIGO and Virgo, and that has some very exciting implications. The rich structure of overtones in a musical instrument can tell you what instrument you're listening to. Similarly, the overtone structure of a black hole ringdown can identify the fundamental properties of that black hole, namely its mass and its spin. The researchers found that they could pinpoint the mass and spin of simulated black holes with much greater precision than if they just used the gravitational wave signal from the lead up to the merger. In astronomy, the analysis of different frequencies of light is called spectroscopy. So this sort of frequency analysis of gravitational waves is now being called gravitational wave spectroscopy. Now, for gravitational wave spectroscopy to be actually useful, probably we'd want to look at some real black hole mergers. And yes, the team totally did this, and reported the results in a follow-up paper, adding Will Farr to the team for this one. Isi et al. Looked at the merger and ringdown signal from the largest black hole merger we've seen, which in fact was also the first one LIGO reported. GW150914, a pair of black holes each 30 or so times the mass of the Sun, spiraling into each other from 1.5 billion light years away. The team analysed the harmonics in the gravitational wave ringdown from this event and claim a likely detection of at least one overtone, detected with a confidence of 3.6 sigma. That means it seems very likely that they really did detect the overtone, but to effectively eliminate doubt, we'd want more observations. By analysing the harmonics, the team calculates the mass of the final black hole as 68.5 solar masses. They also get a spin for the final black hole, a so-called dimensionless spin magnitude of 0.69, where the spin magnitude can vary between 0, not spinning at all, or 1, spinning as fast as possible. 0.69 means this is a rapidly rotating black hole, which is unsurprising seeing as it just absorbs the orbital angular momentum of two black holes. Both the mass and the spin derived from the ringdown are consistent with the estimate that was previously obtained by analysing the entire waveform, but ignoring the overtones. This is important because the overtone analysis only looked at the ringdown. So this tells us that all of the information on the nature of the final black hole properties is embedded in those final oscillations. And that brings us to the last, perhaps coolest application of this technique: testing Einstein. General relativity predicts that black holes should be completely defined by three properties: their mass, their spin, and their electric charge. It doesn't matter what fell in to make the black hole, atoms, photons, dark matter, monkeys, all of that information should be lost, leaving only three properties. And this is the so-called no-hair theorem. Black holes have no hair, well, at most 3 hairs, and the astrophysical black holes are also expected to have no electric charge, so mass and spin should define everything, including the nature of the oscillations during ringdown. The researchers test the no-hair theorem by checking whether the frequency of oscillations and the time for the decay of those oscillations agrees perfectly with Einstein's predictions. And they do, at least within the uncertainties of the experiment. The oscillations are consistent with a black hole purely defined by its mass and spin. The authors claim this as tentative support for the no-hair theorem. It's a long way from a confirmation of the theorem, but with the analysis of more black hole mergers, any deviations from the pure general relativity hairless black hole will either become apparent or become less and less likely to exist. But for now, Einstein reigns supreme. And what about all those new mergers? It's been a while since we saw a big press release from LIGO. The last was the incredible binary neutron star merger that was also detected across the electromagnetic spectrum as a giant explosion. Well, rest assured that detections have continued. LIGO and Virgo have been in their third observing run since April 1st, after massive upgrades to sensitivity, and this run will last for 1 year. The LIGO team typically waits until the run is complete to announce findings because it takes a while to fully confirm each signal, but the team isn't nearly as secretive as they once were. LIGO has a publicly available alert system so that astronomers can follow up gravitational wave detections with other telescopes. LIGO's gravitational wave candidate event database reveals many candidate detections, many of which will prove to be real. So far, the list of high confidence events includes around 20 new black hole mergers, a few black hole neutron star and neutron star mergers. The observatories are seeing a new event roughly every 5 days on average, but sometimes on multiple days in a row. And on August the 28th, 2 black hole mergers were seen separated by only 20 minutes and potentially in the same part of the sky. This is currently looking like just a coincidence, but if not, it'll be hard to come up with a plausible explanation for why 2 pairs of binary black holes should merge near each other at the same time. So, long story short, the initial promise of LIGO and the first detection of gravitational waves really seems to be panning out. Gravitational wave astronomy is now really a thing. We're seeing many mergers of black holes and neutron stars. We're learning an awful lot about these objects. And with the new subfield of gravitational wave spectroscopy, we can now listen to the harmonics of ringing black holes and through them better understand the fundamental nature of extreme spacetime. Whether you want to know the number of possible multiverses or the likelihood of aliens, to challenge yourself in the advanced levels of science, you're going to need to have a solid understanding of probability. Brilliant.org has a new course on probability fundamentals that includes interactive challenges and problems to solve. Honestly, that's the only way to get math, to do it. You can learn probability basics such as fairness, expected value, and symmetry in their course, Probability Fundamentals. Effective learning is about problem solving. To learn more about Brilliant, go to brilliant.org/spacetime.
Hey, Vsauce, Michael here, and today we are going to go inside a black hole. It's not going to be comfortable, but it will be pretty fun. Now, first things first, mathematically speaking, anything could become a black hole if you were to compress it into a small enough space. That's right, you, me, this camera, everything in the universe has what is known as a Schwarzschild radius, a tiny amount of space that, were you to collapse the entire mass of the object into, its density would be so great that its gravitational pull would be so great that not even light could escape from it. You would have a black hole. If you were to compress Mount Everest into something smaller than a nanometer, you would have a black hole. And if you were to compress the entire Earth down to the size of a peanut, you would have a black hole. But fortunately for us, there is no known way to compress Everest or Earth in that fashion. But a star, many times larger than our own sun, has a much larger Schwarzschild radius, and when it runs out of fuel and can no longer keep itself hot enough, it collapses to a single infinitesimally small point known as a singularity. Its density will be infinite, and so its gravitational pull will be so strong that nothing can escape, not even light. But enough about ways black holes form, let's jump into one. First question, what would it look like from the outside? Well, we know that gravitational fields bend space and time. Stars behind our sun will actually appear to be in slightly different locations from Earth because the sun's gravitational field bends the light coming from those stars. When it comes to the gravitational fields of larger objects like entire galaxies, or for that matter a black hole, the effect is even nuttier. Light coming from objects behind them is significantly distorted, producing smears and smudges. As seen from Earth, the blue galaxy behind this red galaxy is completely distorted like a funhouse mirror, so rather than appearing as it really should, it looks to us like a ring, a smudge all the way around the red galaxy. This is known as gravitational lensing. Now take a look at this simulation of a black hole with a galaxy millions of light years behind it. The galaxy is not really in danger of the black hole's suck, but the light coming off of that galaxy certainly is. Watch as the galaxy passes behind the black hole, and its light is contorted, twisted, and distorted. Now here's a really fun demonstration. What if the Earth were to orbit around a black hole? Looking from the outside, the Earth would look normal at first, but as soon as it passed behind the black hole's gravitational field would warp the light reflecting off the Earth, producing this. For the sake of simplicity, let's jump into a simple black hole, one that doesn't have a charge and isn't moving, and also isn't already sucking up a bunch of matter, so it's just there on its own. As we approach, the distortion of the sky grows greater and greater. A larger and larger portion of our field of view looking forward into the black hole will be filled with darkness. At this point, where half of our field of view has been swallowed up in darkness, we have reached the photon sphere. At this point, light is not going to necessarily get sucked into the black hole, but it doesn't necessarily leave it either. Instead, at this magical point in space, light, photons, can actually orbit the black hole. If you were to stop here for a moment and look to the side, you could theoretically see the back of your own head, because light reflecting off the back of your head would travel all the way around the sphere of the black hole right back to your face. A gravitational field not only warps space, it also warps time. Now, for most intents and purposes here on Earth, we never have to worry about that. But near a black hole, gravity would be so strong that an observer standing, watching you jump into the hole, would see something quite strange. They wouldn't see you get sucked quickly into the hole. Instead, they would see your approach become slower and slower and slower until you reached a point known as the event horizon. This is a point in space where, once crossed, there's no going back. It is at that point that light can no longer escape. And so to a person watching you fall into the hole, that would be where your journey ended. You would seem almost frozen in space, the light coming off your body becoming increasingly red-shifted until you simply faded into nothingness. They would never see you cross the event horizon. But for you, of course, everything would seem fine and dandy. You would continue past that horizon to your now inevitable death. As you continue to approach the black hole's singularity, your view of the entire universe would get compressed into a smaller and smaller point in space behind you. If the black hole we're jumping into is large enough, things might actually be quite comfortable at that event horizon. We'll know that we're never going to escape and that our lives are pretty much over, but it might take us hours to actually reach a point where things started to hurt. Why would they hurt? Well, the closer you get to the singularity, the more significant the difference in gravitational pull is across space. And so parts of me that are closer to the singularity would be pulled more strongly than parts that were facing away, and my entire body would be stretched toward the singularity. The effect would be so incredible, scientists don't usually call it stretching, they call it spaghettification. Once you reached this point, you would be dead. Your molecules would be violently ripped and stretched apart, and when they got to the singularity, well, we don't really know what would happen. Perhaps they would completely disappear in violation of all the laws of physics, or maybe they would reappear elsewhere in the universe. It's believed that a moving or spinning black hole might actually create what is known as a wormhole, a way of transitioning across space faster than light. Not in any way that violates the laws of science, but in a way that takes advantage of the universe's dimensions. For instance, if I wanted to get from this point to this point, I'd have to travel the distance. But theoretically, a wormhole would do something really crazy. For instance, this. Now, the 2 points are right next to each other and I can travel between them almost instantaneously. But again, this is all theoretical. Luckily, we do have a possible way of analyzing black holes right here on Earth. Enter the dumb hole. Just as a black hole does not permit light to escape, a dumb hole is an acoustic black hole. It won't allow sound to escape. It doesn't have to be nearly as powerful, and scientists have been able to create dumbholes in laboratories using special fluids traveling at the speed of sound. A lot of progress still needs to be made in the world of acoustic black holes, but we may be able to learn an amazing amount of information about how black holes work by looking at how sound is treated in a dumbhole. Now here's another good question. What would it look like to travel at the speed of light, say, toward the sun? Well, surprisingly, you wouldn't just see the sun immediately rush up toward you. No. In fact, initially, it would look almost as if the sun were receding away from you. Why? Because your field of view would vastly increase in size. You would be able to see stuff almost behind you, and here's why. As you sit there, not moving yet, looking at the sun, there's light coming from stuff behind you. But if you travel the speed of light, you will actually reach that light coming from things behind you. As you reached light speed, your field of view would expand like this, concentrating the stuff in the middle. But where are you in the universe? Or here's a better question, where is the center of the universe? Well, this might sound crazy, but it's everywhere. This is known as the cosmological principle. No matter where you are in the universe, everything else will seem to be moving away from you, expanding at the same rate. The universe is expanding, but not like a balloon getting bigger with all the people inside it. Instead, it's as if we are the surface of a balloon. If you were to put a bunch of dots on a balloon and then blow it up, all of the dots would move away from each other at the same rate. And on the surface of the balloon, there is no center. Take a look at these two layers. They are exactly similar, except the top layer represents a 5% expansion of the bottom layer. Let's say that you live on one of these dots, and you want to measure where everything's moving away from. Well, watch what happens when I line up a dot in the past and the present. Boom. It looks like the center of the expansion. I can do this with any dot. As soon as I choose a dot to be the frame of reference, it immediately becomes the center of the expansion. So while dying in a black hole would be lonely and scary and morbid, when you look up into the sky, think instead about this. No matter where you are or who you are or what your friends or your parents tell you, you really scientifically are the center of the universe. Finally, what if our universe was a Googleplex meters across? It is nowhere near that large, but if it was, it would be so voluminous that statistically, it would be nearly impossible for there not to be an exact copy of you somewhere else out there in the universe. To see why, I highly suggest that you click right there and check out Brady Haran's new channel, Numberphile. It's part of the YouTube original channels, and I've worked with these guys before. They're amazing. They're my favorite kind of geeks. So check out that video, watch their other stuff, and if you like math, I highly suggest that you subscribe. And as always, thanks for watching.
Hey Vsauce, Michael here. This point of light in the sky is Earth, as seen from the surface of Mars. And this is Earth as seen from Saturn. Here's an image taken only 45,000 kilometers away, the famous blue marble. But what does Earth really look like? Well, it depends on how you define look. The word look comes from the old Breton word lagud, meaning eye, the human eye. And that's part of the problem. Images like this are based on light humans can see, but we don't see everything. There's a fantastic episode of Radiolab that uses sound to illustrate just how different other creatures' visual spaces are from our own. When we talk about the way something physically looks, we are talking about the visual perception of emitted or reflected electromagnetic radiation, specifically visible light. Light we perceive as red has a longer wavelength than blue or violet. But what if I crank the wavelength even shorter? Does it stop being light? No, it just becomes light you can't see. Ultraviolet, X-rays, gamma rays. Going the other way, you get infrared, microwaves, and finally, radio waves. In principle, the spectrum of possible electromagnetic wavelengths is infinite. But even within the range of wavelengths we observe, the breadth is breathtaking. If the entire practical spectrum of wavelengths was laid out linearly from New York to Los Angeles, the visual portion we see would only be the size of 100 nanometers, small enough to slip through a surgical mask. Point is, when it comes to what there is to see, our eyes miss out on a lot. For instance, take a look at a remote control. Many of these things communicate with light of wavelengths we can't see, but mobile phone cameras can. Try this at home. Push a button on a remote control and you won't see much, but use a mobile phone camera to detect wavelengths you can't see and have them rendered visible. There's a whole lot going on we miss out on. Our night sky is full of frequencies we can't see with our eyes alone, but Chromoscope.net allows you to extend your vision. This is the Milky Way as we see it, the visible light it gives off, but slide to see how it would look if our eyes sensed other frequencies. Of course, we are having to represent these other frequencies with visible colors, because even electromagnetic pretend time is bounded by our puny limits. As for Earth, if we only saw infrared frequencies, it might look something like this in our minds. Ultraviolet and extreme ultraviolet vision would return unrecognizable spheres. With X-ray vision, auroras around the poles would shine brightly, and gamma-ray vision would give Earth a bright edge from high-energy electromagnetic radiation hitting the atmosphere at a shallow angle. So, which view is correct? Is there an absolute true appearance of the Earth? We haven't even started yet. Look back at the blue marble. What's with the tyranny of north meaning up? Perhaps it's because we often equate up with better, and many early map makers were from north of the equator. But upside-down maps are equally true, no matter how strange they may seem to us. Funny enough, the famous blue marble itself is a product of north equals up bias. It didn't originally look like this. The crew of Apollo 17 originally took it like this. NASA rotated it to fit our traditional idea of up after the fact. Here's a visual of Earth that comes from the US Naval Observatory's live animation of our planet. You can see exactly what parts are in its shadow at this very moment. Other shadows fall on Earth as well, like the moon's shadow. Last week, Bad Astronomer shared this image. The dark smudge on the left is actually the moon's shadow during a solar eclipse as seen from above Earth. There's another problem with the blue marble. It's flat, and the Earth is three-dimensional. A globe is the best way to represent the Earth, but globes are difficult to carry around, and even when displayed in 2 dimensions, well, you just can't see everything at once. A flat map of the Earth is really convenient, but it requires projecting a globe onto something flat, and a sphere's surface cannot be represented on a plane without distortion. The West Wing famously pointed out the limitations of flat maps. There is no such thing as a perfect flat map of the entire world. Some maps are useful for some things and other maps for other things, but it is really fun to pick on the Mercator projection, mainly because it's so popular, and is even used by Google Maps, mainly because it's so easy to zoom in on. It preserves shape decently well, but suffers when it comes to area. As I've shown before, Africa is huge. Its area is so large, the entire contiguous United States could fit inside of it, along with all of China, India, Japan, and much of Europe. But on the Mercator projection, scale near the poles is pretty wonky, distorted, which means Greenland appears to be as large as Africa, even though in reality it is only 1/14 the size. There's more. Check out Alaska and Brazil on a Mercator projection. They appear almost the same size, but in reality, Brazil is nearly 5 times bigger than Alaska. Areas near the equator are minimized, whereas areas closer to the poles are exaggerated. To have fun with this problem, play the Google Maps Mercator puzzle. The red pieces are countries projected outside of their usual locations. Now, what the heck is this weird shape? Well, let's pull it away from the North Pole where scale is distorted a lot, and oh, it's Australia. You can see how the math behind map projections distort Earth by interacting with them on Jason Davies' brilliant site. Notice how small Greenland appears on the Mercator projection when pulled down to the equator, and how exaggerated it becomes when moved to the edge. To be fair, the Mercator projection is great for navigation. If you want something that is more fair when it comes to area, try the Gall Peters. Here, land masses are the right relative size, but shape is sacrificed. Everything looks a bit too narrow. Enter the Mulvide. This projection shows equal areas and is a bit more pleasant shape-wise. If you interrupt the Mulvide around the oceans, relative area is preserved and the shape of land masses becomes even more accurate. When it comes to the shortest route between two places on the surface of the Earth, mnemonic projections are really cool. Every straight line journey taken on Earth's surface is actually part of a great circle. On Mercator projections, actual straight line paths look curved, but every straight line on a mnemonic projection is also a straight line in real life, the shortest route. If you want a compromise between shape and area, you might try the pleasant Winkle Triple, which the National Geographic Society has used for maps it produces since 1998. Or a beautiful butterfly map that can be a ball until it's flattened, say under a pane of glass. The Dymaxion map can unfold to show how nearly connected Earth's landmasses are. It's a great way to visualize human migration over time. It's quite impressive how far and wide humans have traveled on Earth, but it remains a bit of a disappointment to realize just how narrow our slice of visual perception really is. But don't feel bad. This brings us to the story of Julian Bayliss. Yes, hello, is this Dr. Julian Bayliss?
Yeah, speaking.
Bayliss told me about how one day, while using Google Earth, he spotted some dark green vegetation. It looked like a rainforest. An expedition was scheduled, and it turned out to be just that, a rainforest we had previously never seen. I asked him more.
So what have you found there?
To date, we found about 12 new species, just from Marbu. So we found about 3 snakes, 2 chameleons, a bat, about 4 butterflies, 2 new species of plants. And we've only really just been into the forest edge. So I read a paper the other day, a scientific paper. They estimate that there's maybe 8.5 million species in this world, but we've only actually discovered 1.5 million, or between 1.5 and 2 million. So we've actually only discovered maybe 1/5 of everything that's living on this planet.
Wow, our eyes only see a tiny fraction of what there is to see. But within that tiny fraction, there are still an enormous number of things left to find. So keep searching, keep looking.
And as always, thanks for watching.
Excuse me.
Hey, Vsauce, Michael here. Earth only contains 1,066 people. Earth, Texas, the only place on Earth officially named Earth. There are at least 2 places named Moon, but the Earth only has one astronomical moon. Or does it? From September 2006 to June 2007, Earth had an additional moon named 2006 RH-120. It's a near-Earth asteroid that usually orbits around the Sun, but for 13 months, it fell into an orbit around our planet and became another moon of Earth. We can call it that because technically a moon is just a natural satellite.
Yes, I would like
Something in orbit around a planet that humans didn't put there. There's no official minimum size requirement for moon status. The moon? It's a moon. Sputnik, Space Junk, the International Space Station? Not moons, they are artificial satellites. Astronomers believe that most of the time, Earth has additional moons. These newcomers don't always stick around that long, and they tend to only be about a meter in diameter, so we don't always detect them, and they could less sensationally be called temporary asteroid moons, but the vagueness of the word moon means that yes, technically Earth usually has more than one. Oh, and Earth is booking it. I mean, we are moving through space incredibly quickly. A light year is an almost unfathomable distance to put into human terms, but our solar system orbits around the center of the Milky Way at about 782,000 kilometers an hour, which means that from the perspective of the center of our galaxy, about every 1,300 years, Earth travels an entire light year. In other words, the Great Pyramid of Giza wasn't just built 4,500 years ago, it was also built almost 3.5 light years away. Big deal. What's it all worth? Could we assign a price to the entire planet, to Earth itself? Well, Greg Laughlin, an astrophysicist at the University of California, Santa Cruz, devised a beautiful equation for assessing the value of exoplanets we discovered. It considers their habitability, their ease of being studied, and of course, how much money we've already spent looking for them. Funny enough, you can solve for Earth and find out that compared to what we've already spent looking for exoplanets and what we know about them, Earth is worth about $5 quadrillion. The History Channel famously stuck to Earth and rang up all of Earth's resources like water, lumber, and granite. Using the current market prices, they arrived at a total of $7 quadrillion. If you removed and isolated all of the elements your body contains and then sold them each at market price, you could fetch about $2,000. Reddit user Shady Potato applied this math to Earth. If we could mine the entire planet and separate out all of its pure elements, and prices didn't change because of that, we could sell it all for $15.8 sextillion. Of course, calculations like these don't include every single possible thing Earth or any other planet has to offer, and they also don't consider supply and demand. If someone here on Earth, or some extraterrestrial group of planet shoppers, had quadrillions, sextillions of dollars, or the equivalent amount of power, well, they would have the option to shop in a much larger store. For crying out loud, there are more than 10,000 asteroids right here near Earth, and just one of them, 433 Eros, is estimated to contain a $500 quintillion worth of platinum alone, and by weight, even more iron. So to be more realistic, instead of calculating Earth's value on Earth, let's calculate its value on the galactic marketplace, or the universal marketplace. If you, or some hypothetical group of aliens shopping for a planet, could pick any planet in the entire Milky Way galaxy, what about Earth would make it worth anything? The Milky Way galaxy is estimated to contain a supply of around 100 to 400 billion planets.
As far as Earth analogs go, Kepler space mission data suggests there are probably 40 billion Earth-sized planets orbiting within habitable zones of stars in our galaxy. And within the observable universe, quadrillions. So from a raw materials and habitability standpoint, Earth probably isn't that rare. But Earth does have some unique selling points. For one, it's probably the only planet like itself within at least 12 light years, so its location might be prime real estate for an intergalactic rest stop or eminent domain. And secondly, statistically speaking, life as we know it might not be unique to Earth, but there probably isn't life elsewhere that formed exactly like it did here, with jaguars, palm trees, and hairless bipeds who made the same buildings and jokes and art and music that we have. These might be the truest unique selling points for Earth. Aliens wouldn't have to understand or appreciate any of it. If it merely amused them, it might be worth purchasing as a sort of museum or zoo at the least. Of course, interstellar planet shoppers wouldn't have Earth currency to buy it with, and space cash isn't worth anything here. But the technology it would take for them to get to us would likely be at least thousands of years ahead of what we currently have. So, an equitable trade might be, say, limited use of Earth in exchange for their knowledge, or full use or abuse of Earth in exchange for their knowledge, and fair relocation of all Earthlings to some equally habitable exoplanet. Boy, this type of speculation is totally sci-fi. But you know what's not? The next part of establishing Earth's value. Demand. Despite what Earth has to offer, despite what makes it unique, and despite National Geographic's list of 10 reasons other life forms might want Earth, so far we have received 0 offers. The Fermi paradox formally phrases this puzzle. With so many friendly to life as we know it planets out there, many of which have been around longer than even Earth, why haven't we been visited by or heard from intelligent life yet? Maybe Earth and its intelligent life really are rare and special. Or maybe Earth is so typical, so unremarkable, no other intelligent advanced life forms could be bothered to stop by. But this raises another question. Even if something came by, what makes us think it would make an offer? Why would it consider our wishes at all? In Star Trek IV, the aliens wanted to talk to whales, and humans were just an awkward third wheel. When Thomas Jefferson made the Louisiana Purchase, he didn't ask, say, squirrels in Nebraska for permission. He just did it, and all of those squirrels were suddenly in America, without knowing it. For all we know, that may have already happened to us. Earth could be owned by some larger interstellar landlord. Furthermore, this entire question rests on an even more fundamental assumption. The assumption that other intelligent life forms share our concept of ownership, and the belief that physical things can be bought and sold. Amongst Earthlings, human bartering is pretty unique. Only we have developed complicated, socially agreed upon norms for the barter of goods, the use of currency for goods, or the concept that you can own a piece of Earth's surface. Sure, animals can be territorial, but they haven't developed that into a more rigorous, expansive sense of fair exchange. And when it comes to an individual owning more things than they could possibly hold or defend on their own, well, we humans have systems for that. We can teach some animals to use tokens as currency to exchange for treats, but left on their own, they don't incorporate economic ideas into their regular social lives. At the most, we observe animals bartering amongst each other for services, but not goods. Why? Well, they may lack the cognitive ability required to keep track of long-term transactional histories. But they also lack 2 other extremely important things: communication and enforcement. Services, like grooming, are difficult to steal, so animals can easily trade them. But without a language to facilitate snitching, non-humans can't easily report thefts or devise systems for reporting and punishing violations. Animals create some pretty beautiful things: bowerbird nests, pufferfish circles, termite mounds, or the dramatic costumes decorator crabs fashion out of seafloor debris. But ownership and the right to buy or sell what you make is only as useful as the power you have to enforce it. And if you don't have enough power, someone or something else will make decisions for you. For instance, we have decided that animals don't own the selfies they take. 3 years ago, in Indonesia, a monkey stole photojournalist David Slater's camera. He later retrieved the camera and found that the monkey had snapped these fantastic images. Slater maintained that he should receive royalties from people who reproduce the images, like Wikimedia. But US federal regulators recently ruled that since a non-human animal created these photos, they're officially in the public domain. They belong to all of us. The same goes for selfies taken by elephants, or lambs, or Asian short-clawed otters named Musa. And it's not just selfies at play here. The same goes for paintings made by chimpanzees or dog artists. So maybe Earth is worth quadrillions or sextillions of dollars. Maybe it's worth renting in exchange for technological know-how. But the mere fact that we can conceive of ourselves selling our own planet is pretty incredible. I mean, we don't have a deed to planet Earth. We really only own it via finders keepers.
I'd like to trade some items.
But we didn't stumble upon Earth like a hermit crab in its shell.
Okay.
We really just emerged from it. We didn't build Earth. If anything, its selective pressures built us. Does that mean Earth is sort of like a womb?
Let's trade.
Does that mean us selling Earth would be the same as a child selling his or her parents? No, not really. Because we aren't here for the purpose of leaving, analogous to being born. Honestly, the most fitting metaphor might be not that we are Earth's owners, or children, or one and the same with it, but rather that we are Earth's first willful effluvia. In the context of the human body, effluvia are little emissions of things built up within. They often make us giggle and can be gross. And isn't that what we are? A sometimes messy, stinky presence that is built up within and will one day inevitably, and to an extent already have, discharged out into space. I guess what I'm saying is that putting a price tag on Earth is all speculation. We don't know if we will ever be Earth's salesperson. But what we do know is that we are Earth's first fart. And as always, thanks for watching.
Hey, Vsauce, Michael here. On Earth, the average piece of currency changes hands about 55 times a year. That's about once a week. With that kind of turnover, it's safe to say that statistically, in the United States, out of every 100 pieces of currency, one was most likely touched in the last year by someone who within the next year will commit murder. But how much cash, how much physical currency is there on Earth? First things first, how much cash is inside a bank? Well, according to the FBI, the average successful bank robbery involves $10,000. But that's usually just currency from the teller's tills. In their vaults, the average bank might have anywhere from $10,000 to $100,000, with some larger banks at times carrying as much as a few million in cash. But what about in our homes? How much loose change do we all have scattered on dressers or lost under cushions? Well, it's tough to accurately figure out the exact number, and many of the estimates vary. Last year, Lloyd's TSB announced that in the UK, the average person has about £14 15 pence just lying around. A recent survey by Visa looked at a bunch of countries and included cash left at home, the office, and in the car. Their figures are a tad higher, but agree with the US Treasury's estimate a few years ago that the typical US household has $90 to $100 just laying around. Which means that if just everyone in America scrounged up all of their loose change and put it in one place, they would have $15 billion. That's enough to fund 357 more seasons of Arrested Development. But we are asking about how much cash there is on the entire planet. Well, that amount has a special name. It is called M0. It's an aggregate of all coins and banknotes. DollarDays.org's most recent estimate values this total amount, considering all currencies and countries, at just slightly over the equivalent of $5 trillion US dollars. That number, the value of all of the currency on Earth, M0, is huge. But believe it or not, it represents less than 10% of all of the money we humans have available to spend right away. To explain, we should look at how money is born. In pretty much every country on Earth, one of the ways new money can be born involves a central bank. Now, let's say that in our country, the bank is run by Jake from Vsauce 3. He's really smart and he pays close attention to our economy. If he feels that an increase of the money supply would help us, well, he can just make more money. It's that easy. It doesn't need to be printed as currency to be born. The next step involves the commercial banks, like the Bank of Vsauce. These are the banks that you and I use. All the central bank needs to do is buy some things from these banks using the money it just made, and now the commercial banks have more money. There's another way money can be born. It involves commercial banks and gets to the heart of our question. If I go to the bank and deposit £5, the bank says, fantastic, we will hold on to this money for you, and at any time you want, you can withdraw or spend these £5. The thing is, legally, banks only need to reserve a fraction of the money that they are given. It is known as fractional reserve banking, and it pretty much happens in every country. It means that if someone else comes along, like, say, Kevin from Vsauce 2, and he wants to borrow some money, say £3, the bank can lend him £3. And now whenever he wants, he can spend these £3. But here's the thing. Kevin can spend £3 and I can spend 5 for a total of 8, despite the fact that there are only £5 in the bank. New money has been born. And if we want to count all of the spendable money on Earth, we are going to need to include this type of money, the kind that fractional reserve banking creates. If we include that kind of money, we are now talking about a number much larger than M0. Economists call this figure M1. M1 includes all physical currencies as well as money that people can access quickly, like money in checking accounts. Globally, across all countries and all currencies, M1 is estimated to be the equivalent of 25 trillion US dollars. M2 is an even broader definition of money, and it includes things that you can't necessarily spend right away. For instance, savings accounts or CDs under $100,000. M2 globally is currently estimated to be the equivalent of 60 trillion US dollars. Finally, M3. This is a broad definition of money that includes all currencies, banknotes and coins, checking accounts, savings accounts, small CDs, and really big long-time deposits. In the American economy, the Federal Reserve doesn't even report this figure anymore, but as a measure of eventually spendable wealth, it's real, and if we consider M3 the global money supply, that gives us a figure that is equivalent to 75 trillion US dollars.
Of all that money, how much of it is yours? Well, last week over Twitter, Mark Bodie introduced me to globalrichlist.com. Enter your salary and figure out how you stack up against everyone else on Earth. By the way, you can act just like a central bank and control the money supply yourself. It is illegal, but you can technically increase the money supply by counterfeiting, and you can decrease the money supply by subtracting money. For instance, burning it. If you burn your own money, you become poorer. But because you've decreased the money supply, the power of everyone else's money goes up and they become a tiny, tiny bit richer. Of course, given the amount of money on Earth and the amount that you could probably get your hands on and burn, your effect will be quite imperceptible. One of the largest amounts of cash ever burned was done by KLF, who in the 90s, for reasons no one's still quite sure of, burned £1 million worth of cash. It took them about 2 hours to burn all of that cash, and they recorded the act on video. You could also destroy money by eating it, like the rapper Tyga did. But you probably shouldn't do that either because money is dirty. A study published in Applied and Environmental Microbiology reported that the flu virus can survive on cash for 1 hour to 2 days. And other studies have found that about 7% of cash carries viable strains of dangerous bacteria, like those that cause pneumonia or those that come from feces. That is a lot of germs, and those germs might be high. Studies have found that 92% of banknotes are contaminated with traces of illegal drugs, typically cocaine. In London, that number has been as high as 99%. All it takes is for a few exposed banknotes to circulate normally for all of the cash to become contaminated. Locked within the fibers of a banknote, there's an average of 28 micrograms of cocaine, which means that in 5,000 banknotes, there's enough cocaine for an entire line. These drug traces are nearly impossible to remove from banknotes, so there's little risk of the drugs transferring to your skin. However, they can be detected by drug-sniffing dogs, and on more than one occasion, courts have forced police to return confiscated cash because even though drug dogs detected drugs on the cash, that's just how cash is. As if that wasn't enough, cash is also not nutritious. Termites can eat cash, but to us humans, the ones who love this stuff so much, cash as we know it today, and for that matter, money, doesn't really have any intrinsic value. In a post-apocalyptic world where nothing was stable and survival was a challenge, food, clean water, ammo, weapons, antibiotics, machines, fuel, the trade and exchange and gifting of those types of things would be our economy. When what you use as money has an intrinsic value, it's useful in and of itself, it is known as commodity money. It can also include precious metals like gold, whose rarity makes it likely to be accepted by other people for goods and services. Now, when you can safely store all of your commodities in one place and you don't need to defend them or lug them around everywhere, representative money often makes more sense. Store your valuables in a trusted place like a bank and get some slips of paper from them saying, yeah, I own that stuff. Now you can walk around with some easy-to-carry slips of paper and use those to buy the things that you want. We are now closer to what we call money today. I say closer because almost all money that we know of today doesn't represent any actual useful commodity anywhere on Earth. This note doesn't represent how much food or water or gold or spices or video games I have stocked up in a bank. It just is money. It's called fiat money. Fiat is Latin for let it be done. And that kind of authoritative command is exactly what gives fiat money its value.
The people who make it have decreed that it is valuable. Why? Just let it be done. Because of this, the value of fiat money depends on everyone believing that the people who make it will continue to exist and have the authority that they already do. This means that the value of fiat money, unlike other commodities, can be erased by force. Let's imagine that you live in America and have a lot of dollars. Great job. Well, technically, Canada could invade and declare that the US dollar will no longer be accepted at all. Well, shucks. You now have a bunch of paper, which at best is an incomplete deck of famous American flashcards. The important distinction here is that invading Canadians could technically erase the value of fiat money, but nothing they said or did could make a commodity like gold less valuable. Other countries would still be glad to take your gold and in return give you their own still valuable currencies. No amount of force or authority or laws or rules can make a commodity like potable water any less important to drink or gold any less rare. On the other hand, the value of fiat money depends on our beliefs, what we think. So long as we all believe that fiat money is valuable, it is. This happens all the time. What we believe, what we think we know, can actually cause those things to become true. Actual people, real objects, the way the universe works, and deities like Zeus can exist all by themselves, whether we know about them or believe in them. But some concepts require us to believe in them for them to be real. And if no one believes in them, they literally aren't true. It's called the Tinkerbell effect, and the value of fiat money is an often cited example. But what's really cool is the fact that there are situations where our convictions can actually destroy the very thing we believe in. It's called the reverse Tinkerbell effect, and it describes a situation where as more people believe something, that thing actually becomes less and less true. For example, the idea that driving a car is safe. As more and more people believe this, more people will go out driving, and they are likely to drive less cautiously, ironically making driving less safe. Another example would be the idea that in an election, your vote matters. As more and more people believe this, more people will go out and vote, and the individual weight of each vote will go down. It took hard work and tools to build civilization and find cures and explore our solar system. But we should keep in mind that without doing anything at all, we are still capable of creation. By merely believing in something, we can make it actually, truly real. Other things can actually be destroyed if we merely believe in them. Can you believe that? And as always, thanks for watching. Hey, Vsauce! Michael here. Gregory W. Nimitz registered some land containing $492 quintillion worth of platinum. The land was right here. Well, over here. An asteroid named 433 Eros. Not a single sovereign nation on Earth recognizes human claims to extraterrestrial real estate, but he did it anyway. And then, less than a year later, NASA landed a probe on the asteroid. They called it the first asteroid we had ever landed a probe on. Nimitz called it parking space number 29 and promptly sent NASA a $20 parking ticket. But so far, NASA and the US Attorney General have dismissed the fine, saying that his claim to own the asteroid is without legal merit. But why? Plenty of organizations exist that will gladly take your money in return for land on the moon, Venus, Mars. And if you had enough money to go to the moon, nothing is legally stopping you from moving there, building a house with a significant other, having some kids, and turning your moon house into a moon home. It wouldn't be trespassing or squatting or stealing. The 1979 Moon Treaty says that no one can own any part of outer space ever, but only 11 states have signed it. However, 129 nations have signed and or ratified the 1967 Outer Space Treaty, which says that outer space is not subject to national appropriation. It says nothing about a private individual or a company owning part of outer space. But without the recognition and support of at least one sovereign nation, what does ownership really mean? I mean, I can claim anything I want. I can claim to own Prospect Park in Brooklyn. But just saying that I do, or even moving there and living in Prospect Park, wouldn't entitle me to the rights that usually go along with ownership, unless someone with a bunch of power agreed that I owned it and could enforce that ownership and keep others from claiming to also own it. In the past, explorers had few qualms about claiming to own land, even if other humans were already there, because they had power on their side, namely plenty of guns, germs, and steel. To paraphrase con artist Canada Bill Jones, you know what beats 4 aces? A gun. Or as Loblob pointed out, McDonald's actually does serve breakfast after 10:30 if you have a gun. If you claimed some land on the moon as your own and moved in, would you also have to hire your own lunar police and cislunar military to defend it and to keep others from challenging your claim? Pretty much. That's kind of the problem. Currently, it is risky for individuals or corporations to claim and use extraterrestrial territory because the Outer Space Treaty says that outer space is the common heritage of mankind. It belongs to all of us, and only to all of us. Many interpretations of the Outer Space Treaty predict that powerful things like nations would be reluctant to come to your defense should someone else want to move in or cause trouble or dispute your extraterrestrial claim. Maybe you could get a sovereign nation to weigh in on your behalf by declaring universal jurisdiction, but that would need to be for an incredibly terrible, heinous crime, a crime against all of humanity, not just a dispute over a few space rocks. Catherine Dolderina from the Institute of Air and Space Law at McGill University suggests that considering outer space the common heritage of mankind has slowed space exploration. You see, the Outer Space Treaty was based on the Antarctic Treaty, which says that the entire continent shall never become the scene or object of international discord. Discord is not a good thing, but without an incentive to profit from it, not much has happened there, as opposed to the Arctic, where a resource boom is currently underway. If people felt safer appropriating and taking advantage of space, of celestial bodies, if technological development was more incentivized, would we already have orbiting tourist attractions and lunar hotels? Maybe. But here is what you can currently own in outer space. Stuff you put there, and to a certain extent, orbits. The Outer Space Treaty says that the stuff we left on the moon, anything put into space, remains property of the original owner forever. Orbits around Earth are temporarily granted by the International Telecommunication Union, a UN agency, but they don't work like typical real estate on Earth. When a group of equatorial nations attempted to claim orbits above their land boundaries without planning on putting satellites there, their claim was largely ignored. So you not only need to ask the UN for an orbit and get permission, you also need to use it and fill it. It's a little disappointing that we don't know how lunar real estate works, or if it will. But it's exciting to know that we, within our lifetimes, might have a chance to be part of the solution. A unique generation not visiting space for the first time, but homesteading it for the first time. Here's another unresolved space law quandary. If an alien landed in your backyard, intelligent life from beyond Earth, and you shot it with a gun, dressed it, and then cooked up you and your family some alien meat fajitas, would that be hunting or murder? We literally don't know. On Earth, we have human rights, but there are no alien rights. Maybe it would fall under the category of cultural vandalism, an act that's not necessarily illegal, but is a giant bummer to the rest of humanity. This has happened before, not with aliens, but with paintings. In 2003, the Chapman brothers purchased one of the few remaining sets of Goya's fantastic Disasters of War. Instead of displaying the works for the public, they defaced them by drawing clown and puppy heads on the people. They called the work Insult to Injury. In protest, a man threw red paint on Jake Chapman when he appeared at Modern Art Oxford, but at the end of the day, what the Chapman brothers did wasn't illegal. They owned the paintings. Vandalizing the moon or killing a peaceful alien aren't illegal acts, but just like defacing historical paintings, they seem wrong on some deeper level, especially since, because in most museums, you usually can't even touch the paintings. But who was the first person to touch the moon with their bare hands? I mean, the guys who walked around on the moon wore spacesuits. They had material in between their skin and the moon. Well, to be sure, you already have the moon in your hands. Well, little moons. Lunula, the crescent-shaped area at the base of your fingernail where tissue is thicker and the red vascular structures underneath are more hidden, making it white. And to be even more sure, at the quantum level, touch is problematic. As I've covered before, atomically speaking, matter never really contacts other matter in the conventional sense. You can't truly touch anything. Minute physics called it interaction over a short distance. With that in mind, NASA says that Terry Slezak was the first person to touch the moon with his bare hands. He was a technician in quarantine who accidentally got lunar soil smeared all over his hand while removing film magazines from the astronauts' cameras. But when Armstrong and Aldrin returned to the lunar module after their moonwalk and removed their helmets, they came into contact with lunar dust they tracked in on their suits. They even reported its odor, saying it smelled of spent gunpowder or ashes, possibly because it oxidized on contact with the air in the cabin. Point is, the first few breaths of moon-dusty air that Armstrong and Aldrin took in were our first fleshly contact with the moon. Or were they? Walking around on Earth every day, I am surrounded by material that recently was in outer space. Hundreds of metric tons of extraterrestrial rock falls to Earth every year, some from the moon, but most from asteroids, ejected by a high-speed impact and eventually caught by Earth's gravity. Some pieces are big enough to see, but most are pulverized by our atmosphere during entry into tiny particles that disperse in the air, becoming a tiny fraction of the very dust and dirt we clean up and breathe in every day. There's microscopic space dust, pieces of asteroids, and even the moon all around us. In fact, there might be microscopic pieces of the moon under your bed right now, or even under your fingernails. Which means the first human to have fleshly contact with lunar material was the first Homo sapien hundreds of thousands of years ago to walk on dirt. We are still studying exactly how much cosmic dust is in the air that we breathe every day, but it's safe to say that every once in a while you inhale some material that was recently in outer space, some of which thousands of years ago was on the moon. Was the moon. And just like other particulates in our atmosphere, large enough pieces get trapped in the mucus that protects our lungs, meaning that picking your nose is gross, but every once in a while, a booger could literally be out of this world. And as always, thanks for watching.
Hey, Vsauce. Michael here.
Hey,
This is Earth, as seen from Saturn. That is us right there. And if you look closely, okay, see this little protuberance? That's the moon. This image was taken by the Cassini spacecraft on July 19, 2013 at 21:27 Coordinated Universal Time. The thing is, NASA gave the public advanced warning of when it would be taken, which means that this image of Earth was the first ever taken from space that some people on Earth were actually posing for. Our planet looks so small, insignificant, fragile. I recently attended the premiere of Sky One's upcoming
Just
Beauty
looking
and
to
the
trade a little.
Apocalypse with some cool YouTubers, and it got me thinking. In the show, the characters find out that there are only 34 days left before a comet smashes into Earth that's likely to end humanity. They all react in different, interesting ways, but what would I do if I found out that there were only 34 days of human history left? Okay, my first priority would be to get back to America to be with my family. But after that, I don't really have a bucket list, except that is exactly what I would want to spend my last few weeks doing. Making a list to put in a bucket that I would then send far out into space away from Earth's impending vaporization. The list would contain information about us, all Earthlings, so that if libraries and monuments and YouTube videos were all destroyed, a record would still exist somewhere of what and who we were. Like a stone thrown into a lake, the ripples your life causes last long after you vanish. The tree you planted is climbed by future generations. The books you donated inform future readers. But what if it's not just your stone that vanishes, but the entire pond? Perhaps it's arrogance or vanity, but getting cosmic messages in a bottle out there before the end diversifies our archive and gives a better chance for future alien visitors, or whatever is left of humanity, to find out that we were once here, to show what we learned, maybe even to warn future life forms of what we did or what we didn't prepare for. We have already sent some messages about humanity out there beyond Earth, and if Earth is completely destroyed, those messages will be all that's left of us. What are they? Okay, first things first. How do you write something for the future? I mean, the distant future.
The message might not be found for millions of years or billions.
Carla.
It might be
Really
discovered
bad.
by an audience that's completely different,
Let's
not
see
only
what
in
we got.
language,
Always.
but in senses. What if they can't see or hear or feel or taste or smell like we do? Or at all? What if their bodies destroy the very material we write the message on? What language do you even write it in? Well, in general, math and physics, which are believed to be the same everywhere in the universe, have been what we write outer space-bound messages in. Like the Arecibo message, written by Frank Drake, Carl Sagan, and others, which was blasted towards the M13 star cluster in 1974. It's composed of a semi-prime number of binary digits conveying some info about us, and it should reach the center-ish of the M13 cluster in about 25,000 years. At which point, if something intelligent lives there and detects it, they can respond, and their response will return to us another 25,000 years later. We won't be around for that, but Earth has also been broadcasting its radio and TV signals into space. Currently, it's about 200 light years in diameter. Compared to the Milky Way, it's about this big. Aliens within that bubble could tune in and listen to programs we sent out through our airwaves, but these signals thin out as the bubble expands. Across very large distances, they may be essentially impossible to tune into. Maybe a physical time capsule would be more permanent, but it can't be buried on Earth if Earth is about to be ravaged. A time capsule in orbit might be smart, like Lagios 1, a satellite put into orbit in 1976 that allows for very precise laser measurements of positions on Earth, but also contains a plaque designed by Carl Sagan, upon which is written the numbers 1 to 10 in binary, and the arrangement of the Earth's continents 250 million years ago, today, and their estimated arrangement in 8.4 million years, which is how long we believe the satellite's orbit will be stable. Drag caused by the thin atmosphere up where it orbits and influences like solar activity will eventually cause it to fall back down to Earth, but its plaque will serve as a time capsule, a message from us today to whatever happens to be alive or intelligent here on Earth 8 million years in the future. To put that in perspective, the pyramids were only built about 5,000 years ago. 8 million years ago, there weren't even humans on Earth. The latest common ancestor of humans and chimpanzees was around, though. 8 million years from today, when Lagios returns, what will intelligent life on Earth look like? If Earth's surface is barren of life at that point, Lagios 1 will be alone. But what about satellites in geostationary orbits? These orbits are far enough out that they're much safer from atmospheric drag and could remain above Earth much, much longer than satellites like Lagios. These satellites are our pyramids. They're smaller than monuments built by past civilizations, but impervious to anything that might go wrong on the less stable surface of our planet. If alien archaeologists come by in 1 billion years or so, these satellites may be what their alien encyclopedias use as the picture for the humans article. So far, we have erected about 450 of these geostationary monuments. When such a satellite wears down and ceases to be operational, it takes a lot of energy to slow it down so it can move out of the way and fall to Earth to burn up in the atmosphere. So instead, they're usually pushed into what's known as a graveyard orbit, a shell around the planet where they can be parked without interfering with important operational satellites. It's fitting that we call these graveyard orbits because tombs are often the most stunning things we have from previous civilizations. These graveyard orbits are tombs, in a way, not for kings, but for machines. Junkyards that will outexist the very societies and people they so largely define.
Luckily, a few contain more than just our craftsmanship, they also contain a record. Like EchoStar 16, a communications satellite launched into geostationary orbit in 2012. Aboard it is a silicon disk created by artist Trevor Paglen containing 100 images of Earth and Earthlings. Now, unlike Lagios, EchoStar 16 will likely remain in orbit for billions of years, safe from discord and change down here. But here's the thing. What if our entire solar system is lost? Or what if life out there doesn't decide to ever visit our system? Well, in that case, we have sent interstellar messages. At this moment, so far, there are 11 distinct human-made things on trajectories out of the solar system into interstellar space. They're all related to 5 probes: Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, and New Horizons, the thing that recently made a Pluto flyby. These objects are our most distant hellos. Over the next 10,000 million, billion years, they'll pass close enough to other star systems, maybe even planets, to possibly be discovered by other intelligent life forms. We had the foresight to include special messages on these probes. The Pioneer plaques are attached to Pioneer 10 and 11, which, launched in the early 1970s, were the first human-made objects to ever be sent on a trajectory to not just leave Earth, but to leave the solar system entirely. If discovered by other life out there, these plaques, designed by Frank Gregg and Carl Sagan, could be our first chance to say, "Hello, we exist," or, depending on how long humanity lasts, our only chance to say, "Hello, we existed. This is what we were." But will the plaques make sense to aliens? Many human scientists have had trouble deciphering their meaning, but here's what they say. At the bottom is a map of our solar system with a path showing the Pioneer probe itself and where it came from. This element has been particularly criticized for being human-centric. I mean, an arrow? Who's to say aliens will know that this depicts a path and not some structure in our solar system? Also, it's an arrow. Arrows might convey this way only to civilizations that hunted or developed pointy projectiles. Anyway, up here we define units. You can't tell aliens about humans or Earth by using seconds, kilometers, or light years because we made those measurements up. Instead, the plaque uses hyperfine transitions to communicate distances and time. The hope is that curious, intelligent life forms who find this will understand that this is a hydrogen atom. 1 proton, 1 electron. Hydrogen is the most abundant element in the universe, so hopefully its properties will be a common point of understanding. Now, sometimes, if you've got enough hydrogen around, you can catch atoms in the heap transitioning between particles with parallel spins and anti-parallel spins. Now, whenever this transition happens, electromagnetic radiation is released with a period of about 0.7 nanoseconds and a wavelength of about 21 centimeters. It's hoped that aliens equate this tick mark with these 2 units of measurement. For example, the woman is said to be, in binary, 8 of these units tall. 21 centimeters times 8 is 168 centimeters. You would think that putting the probe itself behind them for scale would be enough to show our size, but having both might help solidify the connection. This diagram is meant to show where we live. We are in the middle. The direction and proportional length of the lines show where distant pulsars are. A tick mark near the ends of each line shows the 3rd direction, behind or in front of the plaque, that the line should go in. In binary, next to each line is the period of each pulsar, again, in the time units described above. If aliens make this connection, they could possibly match the periods with the correct pulsars in real life, triangulate our position, and come say hello. Also, since the period of a pulsar changes over time,
they could use our observed periods to date back how long ago this plaque was made. So that's how the plaque works. It kind of feels like we're just sending out a bunch of science homework to space, but how else can you find common ground with something that might not resemble you in any way you could even imagine? Despite heading out first, the Pioneer plaques are not the first physical messages made by us to go interstellar. That title belongs to Voyager 1. Currently moving at 17 kilometers per second, it is the most far-out thing humans have ever made. Literally. In about 40,000 years, both Voyagers will pass within less than 2 light years of other stars, if aliens find them, or if future humans find them. A golden record is attached to both that contains information about humanity. The record is made of gold-plated copper with an aluminum cover containing some uranium-238. Given its half-life, smart aliens could analyze it to determine how long ago the record was made. On the record is the inscription, "To the makers of music, all worlds, all times." The record contains 116 images, as well as audio and video recordings of humans, animals, songs, and greetings in 55 languages. Printed on the record are instructions for playback and info about us. The hydrogen hyperfine transition unit definition and the pulsar map included on the Pioneer plaques, but the record also comes with a stylus and platter to play it. Instructions for using the stylus are on the record. This is a picture of the stylus being used correctly, and then in binary, using the transition units, the record tells the aliens that the stylus should go around the record once every 3.6 seconds to play back correctly, and in total should take about 1 hour to do so. For the video portion, instructions are given and a circle, the first video image, is displayed so they know they did it right. Also included on the record is a message from then President of the United States, Jimmy Carter. There's something vulnerable about the message. It's delivered to an unknown recipient, like when someone in a horror movie asks into the darkness, "Is anyone there? Hello?" This is what it says. "We cast this message into the cosmos. It is likely to survive 1 billion years into the future, when our civilization is profoundly altered and the surface of the Earth may be vastly changed. Of the 200 billion stars in the Milky Way galaxy, some, perhaps many, may have inhabited planets and spacefaring civilizations. If one such civilization intercepts Voyager and can understand these recorded contents, here is our message. This is a present from a small, distant world. A token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope and our determination, and our goodwill in a vast and awesome universe." Are these messages enough? Should we send more? Well, why not send everything? We could if we sent the Library of Babel. It's a website built by Jonathan Basile that currently offers everything that has been or could be written. Seriously, divided into pages, it is built to produce and locate on demand any 3,200 character combination of English letters and the comma, space, and period. Basile has organized it all into hexagon-shaped rooms, each with 4 walls of books containing 5 shelves with 32 volumes of 410 pages each. Everything's arranged in a pseudo-random fashion, so browsing the online library feels like a treasure hunt. Here's how it works. Each page is given a unique sequential page number in base 10. The text on each page is encased inside this number.
An algorithm Basile created uses the page number as a seed to generate a unique big number. That output is then converted into base 29 so that it can be represented using every letter in the English alphabet, as well as the comma, the space, and the period. This is what you see on the page. Basile has made sure that the algorithm will produce every possible combination, and the same page number will create the same output every time. Which means that what is on each page is already predetermined. So, in a way, every page already exists. It only needs to be looked up. And here is the really mind-blowing thing. The contents of a page can be converted to base 10, sent through the inverted algorithm, and turned into the exact page number they're found on. It's a truly eerie experience, because you can find the permanent location for any 3,200 character text. You can find in this library the description of your birth, every possible description of your death, every poem, every joke, every lie, anything that could be said can be found on this site. This thing blurs the line between invention and discovery. Did you really discover or invent that thing if its description already existed? 10 to the 5,000 different pages are offered by the Library of Babel. In comparison, there are only 10 to the 80 atoms in the observable universe. I searched for what I've just said, and sure enough, in this hexagon, on this wall, this shelf, in this volume, on this page, it's there. Hello. But deep down, we feel like there's a difference between this program permuting something unknowingly and a person actually meaning it, intending it, saying it because they wanted to with agency. We use a finite number of symbols to say things. For that reason, a library of every finite combination of those symbols can be made. But just because it can be made doesn't mean it has been said. That is the power we have. Perhaps you and I were born too late to explore the world and too early in history to explore the stars, but we were born at just the right time, which is pretty much all times ever, to explore language, to explore what can be said. What should be said? What should we send out to space? What that can be said will you be the first to say? And as always, thanks for watching. To watch the trailer for You, Me, and the Apocalypse, click right up there, and to see some other cool things YouTubers have done inspired by the series, well, you can also click right over there. Colin Furs is building a giant apocalyptic bunker in his backyard, like for real, it's huge. Also, the Dictionary of Obscure Sorrows has weighed in. Check those out, and thanks for watching.
Is Earth the only planet of its kind in the universe? Or is there somewhere else, like this, out there? Is there life beyond Earth? The search for alien life is one of humankind's greatest technological challenges. And scientists are seeking new ways to find answers.
We're pushing the boundary of information of where life can exist past the Earth and out into the solar system.
Leading the search are sophisticated telescopes that scan the sky, and an armada of robotic probes exploring the outer reaches of our solar system, all revealing the planets, moons, asteroids, and comets like never before.
We can go places and see things that there's no other way we could have ever seen.
The search reveals evidence of strange and unexpected worlds. Places with lakes, storms, and rain. Violent places driven by powerful forces deep underground. Worlds that may have hidden oceans hundreds of millions of miles from the heat of the sun.
The pace of discovery just in the last couple years is just mind-boggling.
New missions are helping to unlock the mysteries of what makes a planet habitable, raising the question of whether the building blocks of life are more prevalent than previously imagined. Not just in our own solar system, but possibly throughout our galaxy.
We now have, for the first time in human history, definite planets out there among the stars that remind us of home.
Finding life beyond Earth. Up now on Nova.
Major funding for NOVA is provided by the following.
After a 7-year, 2 billion-mile voyage, the spacecraft Cassini enters orbit around Saturn. Cassini heads towards the largest of Saturn's 62 moons, Titan. Bigger than the planet Mercury, Titan is hidden by a thick orange haze. No one has ever seen its surface. But a small probe named Huygens, released by Cassini, is about to change everything. This mission will challenge long-held notions of where life could exist beyond Earth. These are the actual images Huygens takes as it breaks through the clouds and haze. Titan is a land of mountains and valleys, a place that looks surprisingly like Earth. Then, images reveal something no one expects. The surface is littered with smooth rocks, the type normally found in riverbeds on Earth.
My response was shock. We look out on the surface and we see what looks like a desert. And at the same time, the data from the probe told us that the ground around the site was wet.
Hundreds of miles overhead, Cassini's radar sweeps the surface. The images show a landscape covered with what appear to be hundreds of lakes. This one covers an area of 6,000 square miles, about the size of Lake Ontario, one of the Great Lakes. It's a surprising discovery.
It's the only world, other than the Earth, that has a liquid on its surface.
But what exactly is this liquid? Titan is minus 290 degrees Fahrenheit. If it's water, it should be frozen solid. Then, one of Cassini's instruments analyzes the infrared light reflected off the lakes. The readings are consistent not with water, but with liquid methane and ethane, substances that on Earth are volatile, flammable gases. The data from Cassini are so detailed, scientists can imagine what it would be like to stand on this cold, distant world.
Standing on the surface of Titan, you see Saturn just sitting there in the sky. A big, huge, stationary object, almost like a door to another dimension. Here we see lakes of liquid methane. And in the horizon, we see mountains. These are mountains made of ice, made of water ice, frozen so hard that it acts like rocks. The features that we see in them are carved by the liquid methane that's forming these lakes. Looking across the horizon on Titan, you might see a thunderstorm or a range of thunderstorms coming at you. We see rain coming down. It's not drops like we're familiar with on Earth. This is methane instead of water. It falls much more slowly due to the low gravity, and the drops are bigger.
So what are the implications of finding a liquid flowing on Titan's surface for a scientist like Chris McKay?
Liquids seem to be the key to life, so maybe there's life in that liquid on Titan. Little things swimming in liquid methane being quite happy at these low, cold temperatures.
There's no evidence that living things like microbes exist in these lakes. But if such evidence were found here, it would fundamentally change perceptions about life beyond Earth. If life could evolve on worlds as drastically different as the Earth and Titan, then perhaps life could evolve in many other ways, on many different worlds. NASA's Director of Planetary Science is Jim Green.
One of the questions that we all want to know, I think deep down inside, is are we alone? I mean, that's really fundamental.
Jim is at the forefront of a global effort to understand whether the conditions for life exist beyond our planet.
We're pushing the boundary of information of where life can exist past the Earth and out into the solar system.
So where in our solar system could life potentially exist? Heading out from the sun, the first planet is Mercury. It's an extremely hostile environment. In March 2011, NASA's Messenger probe becomes the first spacecraft to orbit this small ball of rock and iron. These are some of the first images sent back. Three times closer to the sun than Earth is, Mercury bakes in 800-degree heat on its side facing the sun, while on the night side, temperatures plummet to -290. Mercury is the ultimate desert world. Life of any kind here seems unlikely. Mercury's closest neighbor, Venus, is almost as hostile. Though nearly twice as far from the sun, temperatures here exceed 880 degrees. Decades of observations have revealed a planet shrouded in carbon dioxide and toxic clouds of sulfuric acid. These radar images reveal thousands of ancient volcanoes on a surface hot enough to melt lead, and with an atmospheric pressure that is 90 times greater than on Earth. It is hard to imagine that anything could live down here. But based on chemical analysis of the atmosphere, scientists believe that water once flowed on Venus's surface. If life ever did exist here, evidence has yet to be found. So what is it about Earth, the third planet out from the sun, that makes life possible? The answer lies in three key ingredients. First, all life is made up of organic molecules, consisting of carbon, in compounds that include nitrogen, hydrogen, and oxygen, among others. Although organic molecules aren't alive themselves, they are the basic building blocks of every living organism. Life also needs a liquid, like water. In water, the basic organic molecules can mix, interact, and become more complex. The last ingredient is an energy source, like the sun, to power the chemical reactions that drive all life, from the smallest microbe to us. When these three ingredients came together, billions of years ago, life found a way to take hold. And today persists, even in the most extreme environments, like here. This is the Mojave Desert, Nevada. It is one of the hottest, driest places on our planet.
This part of the desert is particularly interesting to me because it's the driest part. There's an axis of dryness here. If we go either east or west, it becomes wetter.
Surprisingly, even here, with only a foot of rainfall a year, all three ingredients for life are present. The rocks provide just enough shade to prevent water from evaporating completely.
Underneath the white rocks, we can find the most amazing thing. We see this layer of green. This is bacteria. The rock provides a little shelter. It's a little wetter and a little nicer living under the rock than it is in the soil around it. In addition, the white rocks are translucent. Hold them up to the sun and see light coming through. These organisms are photosynthesizing here in the desert where nothing else will grow. So they're living in a miniature little greenhouse.
This place shows that even in some of Earth's most extreme environments, under the right conditions, life has a chance. For scientists like Chris McKay, the question is Earth the only planet with the essential conditions for life? One way to know is to investigate how planets like ours formed to have these ingredients in the first place. That story starts 4.6 billion years ago with the birth of our solar system. As a vast cloud of dust and gas collapses in on itself, pressures increase, temperatures at the center rise to millions of degrees, until energy from the early sun blasts away some of the cloud. This lights up the young solar system, revealing the beginnings of planets. The mystery has always been, how did this spinning cloud of dust become the massive planets we see today?
How does one go from microscopic grains to golf ball sized things? And how do golf ball sized things go from there to 10-meter sized things? And how do those go to planetary embryos? And there's a lot of steps in there we don't quite understand.
Many scientists believe the answers are hidden in asteroids. The oldest rocks in the solar system, leftover debris from its earliest days. In 2003, the Japanese probe Hayabusa sets out on an audacious mission. The goal? To land on an asteroid, collect samples of dust, and then return them to Earth. The target is asteroid Itokawa. 1/3 of a mile long and speeding through space at 56,000 miles per hour. Landing on it would be like trying to hit a speeding bullet with another speeding bullet.
Hayabusa in Japanese means falcon, and the idea was to do like a falcon grabs a rabbit, swoop down, sort of just touch the surface, get your sample, and go.
In 2005, 180 million miles from Earth, Hayabusa makes contact. It stays just long enough to grab a sample. It will take 5 years before Hayabusa returns asteroid dust to Earth. But in the meantime, using lasers on board, Hayabusa takes measurements of Itokawa's size and mass. These allow scientists to determine the asteroid's internal structure. What they discover could be a blueprint for how planets like Earth first formed.
It's not one solid lump of rock, but in fact it consists of a pile of smaller rocks of many sizes, all the way from houses down to dust grains.
If we could see inside asteroid Itokawa, this is what it would look like. A loose mixture of smaller asteroids that are held together by gravity.
Maybe 40% of the internal volume of the asteroid is empty space. You probably could just take your hand and just go like this and just push it down into the asteroid.
Is this the first step in building rocky planets like Earth?
Asteroids are just not lumps of rock. These are the basic parts or building blocks of planets.
Over hundreds of thousands of years, asteroids like Itokawa continue to collide, growing bigger and hotter. As their gravity increases, they attract even more asteroids, until eventually, as temperatures rise, they become spheres of rock with hot, molten cores, protoplanets. Computer simulations suggest that within 10 million years of the solar system's birth, up to 100 protoplanets ranging in size from our moon to Mars were orbiting close to the sun. So why does the solar system look so different today? This is Proto-Earth, 4.5 billion years ago. Planetary geologist Stephen Moisish believes this world was very different from the one we see today.
Looking at the surface here, this landscape is dominated by lava, black and blasted by impacts. Underfoot, we find mostly basaltic rock. It is the frozen product of molten rock. These planetary surfaces weren't molten boiling cauldrons.
But instead, for most of their early histories, they were solid and cool.
The atmosphere is thick with carbon dioxide and laced with sulfuric acid, the result of intense volcanic activity.
The embryonic Earth would have an atmosphere denser than the one we have, and a sky yellow and red and thoroughly unbreathable to us.
How does this toxic and inhospitable world eventually become the Earth we know today? Ironically, it will take a cataclysmic event to create a planet capable of harboring life. A protoplanet the size of Mars slams into early Earth. The collision is so violent, it melts the surface, creates an even larger planet, and blasts molten rock back into space that will coalesce and eventually form our moon. Earth isn't the only planet that gets transformed by giant impacts. Over tens of millions of years, all the protoplanets of the early solar system repeatedly collide, becoming larger bodies with each impact in a destructive game of planetary billiards. This process eventually formed the 4 rocky planets seen today: Mercury, Venus, Earth, and Mars.
And so the final planets that we have today are really the ones that won the competition, and that some planets were literally destroyed or thrown out of the solar system, and others survived to be here today.
Sarah Stewart is a planetary scientist. She's trying to determine how these impacts created a habitable world.
There's some magic set of conditions that has to occur in a solar system to give you an Earth-like planet.
Figuring out what happens when a massive planet the size of Mars hits Earth is no small feat. It requires smashing things together at extremely high velocities.
We want to simulate what happens when materials strike the Earth at very high speeds. What we can do in the lab is study little pieces of the process, and using the information we gather from many experiments, we build computer models that try and recreate the whole event.
This requires a special piece of hardware, a 20-foot cannon that uses an explosive charge to fire projectiles at up to 6,000 miles per hour. At the other end is a pressure chamber and the target, representing a planet like Earth, wired up with precision sensors.
We have a 40-millimeter gun that launches 100-gram bullets into rocks or ices, and we study what happens as that shock wave travels through the material.
The gun is set to fire. Each test measures the temperatures and shock waves generated in different materials when they are slammed into each other. The results are fed into computer models of the final stages of a planet's formation.
Over the past few years, we've realized how important the last giant impact is to the final state of a planet. That last impact could fundamentally change major parts of the planet, and that could lead to something that's Earth-like or something that's more Mercury-like.
Sarah's work, though not yet conclusive, suggests that giant impacts could play a role in producing water on a planet's surface. Her results indicate the collisions were so violent they could heat rock to 2,700 degrees, hot enough to release water trapped deep beneath the surfaces as steam. Sarah believes this may have happened during Earth's final catastrophic collision. In its aftermath, as the raging hot planet cools over millions of years, this steam condenses and falls as rain, covering the surface with seas and oceans. If this hypothesis is correct, then several million years after forming, Earth has 2 of the 3 ingredients needed for life: water and energy from the sun. But what about organic molecules, the chemical building blocks of life? How did they get to Earth? Some scientists believe the answer may lie in the furthest reaches of the solar system. Beyond Jupiter, Saturn, Uranus, and even Neptune.
And Pluto.
Here, 3 billion miles from the Sun, is a vast ring of comets and other debris called the Kuiper Belt. Like asteroids, comets are remnants from the dawn of the solar system. But as well as rock, they are also made of ices that only freeze this far from the Sun. Astrobiologist Danny Glavin and his team think comets are the key to understanding how the final ingredients necessary for life arrived on Earth.
The reason that comets are so important to study is that they really are windows back in time. These things formed 4.5 billion years ago, before the Earth even formed. And so we're looking at the chemistry in these objects that was frozen in time.
But analyzing actual comet material when the closest sample is more than 3 billion miles away is a major challenge. Fortunately, icy comets occasionally fly in closer to Earth. As they approach the Sun, comets warm up and the ice starts to vaporize, spitting out tiny particles of ice and dust.
So when you're looking at a comet in the sky, what you're actually seeing is predominantly the tail. You don't see that tiny rocky ice nucleus because it's being dominated by the sublimation of ices and rocks. So you see that long tail and the solar wind, which is just dragging it for millions of miles behind.
Liftoff of the Stardust spacecraft.
A Delta II rocket blasts into space. On board is the probe Stardust.
On through Mach 1. Twinkle looks very good, burning nicely.
The aim, to meet up with a comet speeding through space at nearly 60,000 miles per hour, then fly through the ice and dust and bring some of it back to Earth. 240 million miles from Earth, Stardust approaches the comet named Wild 2. It heads to the heart of the comet and takes these images of its solid, icy nucleus. The surface is broken and jagged, and shooting out of it are jets of dust and ice particles. Astronomer John Spencer is an expert on objects from the outer solar system.
The cometary surface is pretty treacherous. We have crazy spires that may be several hundred feet high. We have overhangs, we have upturned layers where the surface really seems to have been torn apart. This is a very, very bizarre landscape. We have a surface that is mostly black, but scattered around within that we have fresh ice. We see a mostly black sky because the atmosphere is almost negligible. That black sky is punctuated by these geyser-like jets of ice particles that are shooting up at supersonic velocity.
These icy geysers bombard stardust.
These particles hit at almost 14,000 miles per hour, 6 times faster than a speeding bullet.
Stardust survives intact. And on January 15th, 2006, the samples return to Earth.
The samples fell down on Utah, and boom, we had the first comet sample materials. And there were astrobiologists all over the Earth that were, kind of screaming inside because we knew this was our first chance to actually analyze comet material.
Inside, scientists discover over 1,000 grains of comet dust. Glavin and his team analyze this material for 3 years. Then, they make an incredible discovery. In the dust from the comet are traces of the organic molecule glycine, an integral part of living things. Probably frozen into the comet when it formed, glycine consists of simple elements found in the cloud of gas and dust that gave birth to our solar system.
Now, glycine is an amino acid. It's one of the building blocks for life.
These make life go. They make up proteins and enzymes. They catalyze all the reactions in our bodies. They're fundamental to life. Without these, we could not exist at all.
All life on Earth, from these bacteria to us, uses amino acids.
Heads up.
Glycine is special because it's the most common of the 20 amino acids needed to make proteins, part of the very fabric of life. The discovery means that comets could have been one source of the organic materials necessary for life on Earth.
We proved that, in fact, comets could have delivered the raw ingredients of life to the early Earth.
But what could cause comets to fly in from the furthest edges of the solar system, slam into Earth, and deliver these organic compounds? The clues to one possible process lie back out in the Kuiper Belt, the disk of icy objects that orbits the sun at the edge of our solar system.
We expected when we found the Kuiper Belt that we would just see objects in nice circular orbits about the sun.
But observations reveal that the Kuiper Belt objects are not orbiting as predicted. Out here, it's chaotic.
When we look at the Kuiper Belt, we see something that looks like somebody took the solar system, picked it up, and shook it real hard. And that's what started us thinking that something really strange is happening.
Leveson theorizes that the reason for this mayhem likely is connected with the 2 largest planets in the solar system. Jupiter is so big it could swallow more than 1,300 Earths. And Saturn, with its vast rings of ice, is 95 times Earth's mass. With their enormous size comes an enormous gravitational pull.
Everything that we see is a result of what Jupiter and Saturn did.
Leveson wonders if the chaos of the Kuiper Belt could have resulted from a planet smashing into it. To find out, he runs a number of computer simulations. One model creates the conditions in the Kuiper Belt that we see today. 3.9 billion years ago, as Jupiter circled the Sun twice, Saturn made one complete orbit. Each time these orbits coincided, there was a powerful gravitational surge. That pushed Saturn's orbit further from the Sun. and destabilize the orbits of the two outermost planets, Uranus and Neptune.
Jupiter and Saturn sort of tugged each other, and that drove the orbits of Uranus and Neptune absolutely nuts.
Uranus and Neptune are sent careening outwards towards the Kuiper Belt. Comets ranging in size from a mile across to objects the size of Pluto are blasted out of their orbits by the planetary invasion.
The disk went kaploom. Think of it as sort of a bowling ball hitting bowling pins. These things got scattered all over the place.
The end result is a 100-million-year period when comets, kicked out into the solar system by Uranus and Neptune, smash into anything in their path. It's a period scientists call the Late Heavy Bombardment. Earth doesn't escape.
This was so violent that probably every square inch of the surface of the Earth was hit by a comet during this time.
This is one theory that might explain how massive amounts of organic molecules, the building blocks of life, made their way to Earth. Possible evidence of the Late Heavy Bombardment can be seen on the surface of other planets and moons in the solar system. Impact craters.
Literally, the seeds of life, the amino acids, would have been delivered to all the planets and their moons in our solar system.
So if life's building blocks were delivered by comets throughout the solar system, could life also have sprung up on worlds other than Earth? It is unlikely that living organisms exist today on Venus or Mercury, as space probes have found no evidence on these planets of the other vital ingredient life needs, liquid water. But what about Mars? Organic compounds have yet to be found here, but scientists are searching the planet for the other preconditions of life. There have been many missions to Mars, and nearly all suggest that water once flowed on the surface. These detailed images from satellites orbiting Mars reveal vast canyons blasted out by epic floods, and valleys carved by raging rivers. But the evidence indicates that all this water disappeared from the surface billions of years ago, as Mars cooled down and lost its atmosphere. But on May 25th, 2008, a spacecraft called Phoenix touches down near Mars' North Pole. Digging a few inches down, it exposes a white material that vaporizes after a few days. Soil analysis reveals it is water ice.
We landed 68 degrees north. Poof, just a few centimeters below the ground, there was a layer of ice.
Satellites analyze radar waves bouncing back from both polar caps. They reveal that beneath a layer of frozen carbon dioxide, there is a lot of water ice. If it all melted, it would cover the whole planet in an ocean more than 80 feet deep.
When we look at Mars and we see the reservoirs of water there, it's completely surprised us in terms of the amount of water and how much water is actually trapped underground.
The same satellites orbiting Mars are discovering that buried ice is also widespread beneath the desert floors.
When we look at Mars, we see what looks like a desert world with no water. But in fact, Mars has lots of water. It's ice. Mars is an ice cube covered with a layer of dirt.
But this doesn't mean that finding life here is imminent. Ice doesn't melt the same way on Mars as it does on Earth. The atmospheric pressure here is 150 times lower than ours. It's impossible for water to exist as a liquid at the surface.
Ice on Mars behaves like dry ice does on Earth. A piece of dry ice on Earth goes directly from the solid ice to vapor. It doesn't form a liquid. That's why we call it dry ice. On Mars, the pressure is so low that water ice does the same thing.
No liquid water on the surface of Mars today means that vital chemical reactions cannot take place. It seems impossible that life could exist there. But could it exist in the buried ice itself? An expedition to one of the coldest places on Earth is looking to answer that question. These are the dry valleys of the Antarctic, one of the world's most extreme deserts. Here, beneath a layer of dry dirt, is buried ice similar to Mars. If life can exist here, could it exist on Mars too?
We're doing in the Antarctic exactly what we want to do on Mars. We drill down into this Mars-like soil, we collect Mars-like ice, and we look for what we hope are Mars-like microorganisms.
At the point where the dirt meets the ice, the team discovers a thin film of liquid water. And when they look at the samples under a microscope, to their surprise, there is something moving.
We're finding at the ice there is life, which is quite remarkable.
Microorganisms thrive in this thin film of water, but only for a short time.
They spend most of the year frozen and dormant, and they're only active for a few weeks each summer when temperatures get warm.
On Mars, summer temperatures at the equator can reach 70 degrees. Could the buried ice melt here and create conditions similar to those found in the Antarctic?
We may be able to find conditions where the ice is close enough to the surface, close enough to the equator, that even under today's conditions, there's a small chance of liquid water and life.
If probes were to find liquid water on Mars, it would be an extraordinary discovery. But water alone does not equal life.
There is a better match today between conditions that we know can support life on Earth and conditions that we know either exist or once existed on other planets within our solar system. But that still begs the question, what conditions are required for life to emerge in the first place? How does this process of genesis, life emerging from non-living material, take place? Are the conditions that once existed on Mars adequate for that? We don't know. We simply don't know.
So how could scientists find out if life is possible below Mars' surface? One recent discovery, still open to debate, provides a clue. Measuring wavelengths of infrared light, a NASA telescope on Earth detects something mysterious in Mars' atmosphere. Evidence of methane gas. It's an intriguing find. Some methane gas on Earth is produced by geological activity, like mud volcanoes. But most of the methane found in our atmosphere is a waste product generated by microorganisms.
Methane has a very interesting connection to life in many ways. It could be a product of life. It could be something that life has made, evidence of life.
Well, the discovery of methane was really one of the fabulous discoveries that have come out just in the last several years.
New observations by the Keck telescope suggest that certain areas on Mars are releasing thousands of tons of methane gas every year. So where is the methane coming from?
It's seasonal. We seem to have more methane emitted during the summer season on Mars than we do at any other time.
There is not enough data yet to tell scientists what is producing the methane. But whatever the source, it's a tantalizing clue that could change our understanding of Mars.
Methane could be biological, which would be amazing, or it would indicate that there's some geological process making methane, which would also be amazing, because that would indicate that Mars is an active world.
To find out, NASA is going back to the Red Planet. This time, one of its key missions is to search for organic molecules, the building blocks of life.
If we were to find organic molecules on Mars and confirm that they're actually from Mars, not something we brought along, wow, that would be spectacular.
If found, it might mean that all three ingredients for life are here, opening the possibility that life could take hold.
Of course, we're all human, right? And we want certain things. Nobody wants us to be alone, right? But it's important in science to maintain an open mind.
To find organic molecules, NASA is launching a Mars rover the size of a compact car, named Curiosity.
Curiosity will be our first great chance, I believe, to look for life on Mars.
Curiosity holds the most advanced set of science instruments yet sent to the planet. It will zap, grind, and bake Martian rocks and use spectroscopic analysis to reveal if the samples contain any of the chemical ingredients for life.
It is not just a geologist, it's an astrobiologist. It can look at rocks and everything else around it in ways that we've never looked at the material before.
Even with an advanced set of instruments, finding organic molecules will still be a challenge.
It's going to be a tricky problem. There are lots of processes that can destroy organic molecules. Radiation from space can destroy them. Oxidizing compounds in the Martian atmosphere can destroy them. So you're looking for organic molecules that have somehow been protected from the Martian environment for a while.
And the bar is set even higher because Curiosity will search for specific organic compounds that are the product of living things.
What's that noise? Let's do it.
Evidence that life once existed. That's what Jennifer Eigenbrode's experiment is designed to uncover.
The organic molecules tell a story about where they came from and what happened to them. And that's the story that I'm trying to uncover in Mars rocks.
That experiment may very well change our impression of Mars as a lifeless body and change it to harboring life.
If Curiosity turns up any evidence that life once existed on Mars, it will have enormous implications.
If right here in our own little solar system, life started twice, then it would say that life is just everywhere.
Curiosity and other missions may one day reveal if life once existed on places like Mars, and if it still exists today. But even if scientists ultimately conclude that there is no life on the planets closest to Earth, it doesn't mean it's not out there. Beyond Mars are other worlds, waiting to be explored. The distant moons that orbit the giant planets Jupiter and Saturn. Moons just as strange as the orange-shrouded Titan. one pockmarked with hundreds of volcanoes, others glistening with ice and covered in mysterious lines, and one tiny moon etched with deep fissures.
We're now finding, when we look at these giant planets and their moons, that they are almost like mini solar systems in themselves.
Probes are making discoveries on these moons that are changing our understanding of where life can exist. They're finding evidence of new sources of energy.
What have you got
hidden
to trade
oceans
today?
of liquid water, and organic molecules blasting into space. And far beyond these worlds, scientists are exploring entire new solar systems around other stars.
Surely billions, hundreds of billions of the Earth-like planets out there have the conditions suitable for life.
As scientists race to explore these distant places with more and more advanced technologies, they are finding that the conditions for life are not exclusive to Earth, and that the natural forces set in motion here might be active elsewhere, in our galaxy and beyond. Are we alone in the universe? This age-old question is yielding some provocative new answers. Recent discoveries suggest that the conditions for life might be more prevalent than ever imagined.
Science fiction didn't tell us in any way, shape, or form what we're finding out now.
Missions to our neighbor Mars are revealing evidence that water, a key ingredient for life, may be present.
Mars has lots of water. Mars is an ice cube covered with a layer of dirt.
And probes are finding the essential chemical building blocks of life in unexpected places.
Literally, the seeds of life would have been delivered to all the planets and their moons in our solar system.
But what about the colder outer reaches of our solar system and beyond? Could life exist out here too? New missions are revealing strange worlds, moons that could have vast oceans concealed beneath miles of ice. Landscapes littered with hundreds of active volcanoes.
So now, the zone where life could possibly exist has expanded out from Earth to the outer reaches of the solar system.
And places where jets erupt hundreds of miles into space.
We could hold in our hands evidence for extraterrestrial life.
And the same epic forces that gave birth to our solar system are at work throughout the universe. Tens of billions of planets are estimated to be orbiting other stars in our own galaxy alone. Could there be an Earth-like planet among them?
We will find habitable worlds for sure, if not this week or next month or next year, sooner or later.
Finding life beyond Earth. Up now on Nova.
Major funding for NOVA is provided by the following.
The possibility of life beyond Earth is a tantalizing idea, long prompting our species to wonder if there are other worlds where life exists. Now, as space technology advances, the chances of finding it are greater than ever.
I would love to find life beyond Earth. I'd like to think that we could do that. And I'd like to think that we could do that in the next several years.
The search focuses on 3 key ingredients. The first one is life's basic chemical building blocks, made from simple elements found in the cloud of gas and dust that gave birth to all the planets and moons. These chemicals were possibly delivered throughout the solar system billions of years ago by comets and asteroids. They are compounds called organics, containing carbon, oxygen, hydrogen, and nitrogen. Next, life needs a liquid, like water, that allows these compounds to mix and interact. And finally, an energy source, like the sun, to power the chemical reactions that make life possible. Scientists were once convinced that all 3 ingredients could only be found, if at all, on planets that are at just the right distance from the sun. Too close, and it's too hot. Any further away than Mars, and it's too cold. But now, missions to the outer solar system are calling this assumption into question. This is Jupiter, as seen by the space probe Voyager 1, launched decades ago to explore the outer solar system. 500 million miles from the sun, it seems unlikely that life could exist out here in such extreme cold. Voyager approaches Io, one of Jupiter's more than 60 moons, orbiting in the shadow of the gas giant. Io should be a frozen, icy, barren world, but Voyager spots something completely unexpected. These actual images of Io's surface reveal hundreds of giant, active volcanoes. Later probes expose vast lakes of molten lava.
Let's see what you have.
On Earth, volcanic activity is driven by heat in the interior. But Io is so small that it should have cooled down billions of years ago. There must be another source of energy inside the moon.
The discovery of active volcanism on Io was one of the greatest discoveries of planetary science.
By observing Earth's volcanoes and studying the huge amount of data gathered from Io, Ashley Davies pictures what walking on Io's surface would be like.
Walking across the surface of Io, it's a very, very hostile environment. It's either very, very cold, or it's very, very hot where there's volcanic activity taking place. And of course, there's no atmosphere. There'd be a bounce in your step because the gravity of Io is about the same on the moon, 1/6 of the Earth. You feel the crunch underfoot as you head from one volcano to another across these vast plains. Well, here we are in the middle of a vast lava flow field. It's dark, it's quite hot, This is comprised of lava flows that have erupted from one of Io's many volcanoes, like that one over there.
I just want to trade a few things. New Horizons flies past Io. It takes this photograph of an enormous eruption from a volcano called Tvashtar. A vast plume of sulfur shoots 200 miles into space. These actual images reveal the plume as it spreads out and rains back to the surface.
On Io, we see these large volcanic eruptions. The gases that are coming out of the lava blast this material high into space, into the vacuum of space. It's very, very spectacular.
What could be generating so much energy in a moon that should be frozen solid? And where is the power coming from? The key to understanding Io's volcanic activity is its parent planet, Jupiter. Io orbits Jupiter in a slight ellipse rather than a circle. With every orbit, Io experiences gravitational pushes and pulls from Jupiter and other moons. When Io is closest to the giant planet, it is stretched by more than 330 feet. Over billions of years, this has created an immense amount of friction deep inside the moon.
This continual flexing of the satellite is like bending a piece of metal. It heats up. And this is the ultimate source of Io's volcanic energy and its volcanic heart.
The powerful tidal force generated by the massive gravitational pull of Jupiter creates an alternate source of energy far from the warmth of the sun. A source of energy that could, in principle, support life.
What's so important about Io is that it moves our perceptions away from a habitable zone around the sun where energy is just derived completely from the sun. So now the zone where life could possibly exist has expanded out from Earth to the outer reaches of the solar system.
But the chances of life existing on Io itself are slim. Even though it has an energy source and could have the right chemical building blocks, possibly delivered by comets and asteroids billions of years ago, scientists have not yet detected the third key ingredient, a liquid like water. But Io is not the only moon circling Jupiter. NASA's unmanned space probe Galileo flies by the next moon out, Europa.
It passed by Europa 12 times, and only 12 times. Virtually everything we know about Europa is from those 12 passes, and each and every one of them has excited us beyond belief.
Slightly smaller than our own moon, Europa is covered with ice. Data collected by Galileo shows that the surface is minus 260 degrees Fahrenheit. Surely hostile to life. But as the probe gets closer, it takes these images. A mysterious net